Everyone, welcome to Unit 5.2 video lesson. Today we are continuing to solve systems of equations. We have a new method today called substitution. Okay, so substitution works by taking one of the variables in our system and substituting it into the other equation. Okay, so we essentially need to pick one of our equations where we have a variable that is isolated, which we know means by itself, okay, or you can solve to isolate the variable. Okay, we're then going to make a substitution. So whatever that variable is equivalent to, we're going to take that value and we're going to plug it into the other equation. Very important that you use the second equation in that step, because if you try and plug it back into itself, you will kind of get a nonsense answer. All right, once you do that, you should be left with an equation that is just one variable, which means that you can then solve. Okay, and we're going to solve it like a regular equation. Okay, the only thing we then need to do is plug in and solve for the remaining variable, because the solution to a system of equations is an ordered pair. Okay, so let's see this in action. All right, so I have here my two systems of equations. They look just like they were written in graphing, okay, except today's method is going to be all algebraic. All right, so we can see here that our first equation is isolated for the variable of x, okay, meaning we know what x is equal to. And since we know what it is equal to, we can substitute that into the second equation. Instead of having the x and two variables, if we plug this in, we're going to totally replace the x in the second equation. Okay, so we're going to totally replace that. So that now our equation only has one variable in it. And if it has one variable, then we're able to solve. Okay, so we can distribute and combine like terms so that now we can solve this equation. Oops, and actually I messed up on my distributing here, didn't I? It should be a minus 12. Okay. All right, so now solve. All right, so we have that y equals -3, but remember we're not done because our solution has to be an ordered pair. So we need to know what x equals. Okay, if we use our first equation, we could plug y into that, the y that we just solved for, and it's already solved for x. So we could just evaluate. Okay, now I will mention you can use either equations and you will still get the same answer, but you want to pick the one that's easier for you. Okay, so our final answer is the ordered pair of both variables. So if you compare this to the graphing method, that would be where the two lines would intersect. Okay, now we can check that we did this correctly. Okay, if you remember, An ordered pair is a solution of a system when it gives a true statement in both equations. So if we take our ordered pair of 3, -3 and plug it in to both of our originals, we should get a true statement on each one. And so we know that that final answer is correct. Okay, so now when I'm looking at these two equations, my variable is not isolated. Okay, it's not solved for like it was in the first equation. So you want to look at all of your variables and you want to choose the one that can most easily be isolated for. So I see in my second equation, I can very easily isolate that for x. So I'm going to get x by itself, which means we're going to move the 2y. Okay, well I now know what x is equal to. And I can use that to substitute in to the other equation. Nope, not for the y. Sorry. It's substituting in for the x. So we're going to totally replace the x with what we just solved for. Okay, so how will that look? Okay, so you see we totally replaced the x with the value from the other equation. And now we're just going to solve like regular. Combine like terms and solve. So we have that y equals 1, but remember, you need both variables. Okay, so you plug back in to either equation. Okay, you can either use one of the originals or you can use your rearranged. I'm going to use the rearranged equation since it's already solved for x. I just have to plug in the value of my y and evaluate. So my final answer is an ordered pair 0, 1. Okay, so looking at my next example, so again, none of my equations have a variable isolated, but if I look through, I see that there is one that could very easily get isolated, and it would be the y in the first equation. All right, and that would be because it has a coefficient of 1. So you don't have to divide anything out. All we would have to do is move the x. And now I can take this value of the y. I know what y is equal to. And I can replace it in my other equation. Okay, and now that it's all one variable, we can easily solve the equation. Okay, so I get one variable, and now I want to plug back in and solve for the other. So again, I'm going to use my rearranged equation since it's already solved for y. Okay, so my final answer is an ordered pair, 2, 5. Okay, so sometimes you may have to rearrange the equation in order to isolate. Okay, so this says when variables disappear. So if I had to guess, this is our special case. Okay, so my second equation is the one I'm going to isolate. So I can now substitute in, okay, to the other equation for y. So I'm going to totally replace the y with that expression. Okay. Okay, so as I go to solve 12x minus 12x, that cancels. And I'm left with 40 equals 26. Well, ask yourself, is this a true or false statement now? This is false. So we know that means no solution. Okay, so if we compare this to a graphing situation, how do we get no solution? No solution comes from parallel lines. Okay, so I bet if we took each of those equations and put them into slope-intercept form, which one of them already is, that you would have the same slope in each equation. So we know that same slope, parallel lines, they would never intersect, which is how we get no solution. Okay, let's try another special case here when variables disappear. So I am going to isolate in the first equation. Okay, so I'm going to take that and substitute in. Alright, so combining like terms, 6y minus 6y cancels again. I get 12 equals 12. Well, this now is a true statement. And we know the final answer for a true statement is all solutions. Okay, so again, if we wanted to compare this to a graphing scenario, these would be the same lines. All right, take a deep breath as we move into the last part of our lesson here. We're going to look at word problems. So now when we're given a word problem, we're going to have to write the system of equations for ourselves. Okay, we're going to identify the variables, so what is the problem talking about? And then we're going to identify the totals that are given. Okay, and we're going to use this table trick to help us fill in all of the values. Okay, and once we have our equations, we're going to solve them algebraically. So the school that Molly attends is selling tickets to the annual dance competition. Adult tickets cost $12 and children's tickets cost $3. The school collected $1,158 in ticket sales for the entire competition. A total of 128 tickets were sold altogether. Find the number of adult tickets and the number of children's tickets that were purchased. Okay, so we want to identify our variables. So we're going to have an X and a Y. So what are the two items that this problem is talking about? They're talking about adult tickets and they're talking about children's tickets. Okay, because it says find the adult and children. Alright, so now I want you to create this chart. Okay, so it's going to have 2 rows and 3 boxes in each row. Alright, so we're going to label this as X, which we know is adult. This is going to be Y, which is children. And the last column is going to be total. Okay, so we're first going to look through our problem and we're going to pick out the totals. Okay, so I see one already that actually uses the word total. It says 128 tickets. Now we need to find the other total. It says the school collected $1,158 for the entire competition. Okay, so now when we fill in our X and our Y, the first row is going to be numbers that correspond with tickets, and the second row is going to be numbers that correspond to money. Okay, the money one is probably the easiest. And once we've used a number, okay, it's gone from the problem. So I see 2 other dollar amounts. It says adult tickets are $12 and children's tickets are $3. Okay, so remember adult was my X. So I have 12X and plus 3Y for my children's tickets, which give me that total of $1,158. Okay, so now I've used those numbers. Well, I still have 2 boxes open in my table, and I don't have any numbers left in my problem, which means that this will just be variables. Okay, so we very easily just wrote the equations for our problem. Okay, so X plus Y So now we're going to use substitution to solve this problem. Okay, so I see that my first equation has a variable that I could isolate. And really, you could isolate for either one of those. So I'm just going to solve for X. Okay, and that is what I'm going to substitute in to my other equation. So I'm going to totally replace it. Okay, so this is like just a regular problem like before, now that we've got our equations written. Okay, and we're going to solve. Okay, so I get y equals 42, and remember that y represents children's tickets, and so for this situation to be reasonable, we would need a positive whole number as our answer. Okay, and now we're going to substitute back in to get our x. So I'm going to use my rearranged equation. Okay, I'm plugging 42 in. Okay, so our final answer here is that there were 86 adult tickets and 42 children's tickets. Okay, so for a word problem, we want to put it back into the original context, so we're not just giving an ordered pair. Alright, so that was everything that we need to know for substitution. I hope that we didn't find that to be too difficult. Alright, please make sure your notes are complete, you've written down any questions, and I will see you next time. Alright, thanks for watching, everybody.